So we're going to cover the superposition theorem first, and then shortly thereafter, we are going to see that superposition is simply a larger or part of a larger concept called linearity. Okay, this is a rather long definition. I don't think it's particularly important that you actually write it down word for word. Okay. So the superposition theorem states that in any linear resistive network, the voltage across or the current through any resistor or source may be calculated by adding algebraically all the individual voltages or currents caused by the separate independent sources I'm going to underline independent here because it's important. Acting alone with all other independent sources, independent voltage sources being replaced by short circuits and all other independent current sources being replaced by open circuits. So this is a very long expression, okay? Let me put what it actually means in a more simple form. Let's say that we have a circuit that contains multiple independent sources. It does not matter whether those are voltage sources or current sources. We can find any voltage or current quantity in that circuit by analyzing the circuit with each independent source on by itself and all other independent sources turned off, and then simply add the results up at the end, and we would get the exact same response. So I'm going to prove that to you. We're going to analyze the circuit. It's not going to be anything particularly wild here. Let's say that we have a 6-volt source in series with a 6-ohm resistor. Here we have a 10-ohm resistor here we have a 9 ohm resistor. Here we have a 2 amp current source like so. The quantity that we are interested in, let me use the correct notation here, will be the current IX. Okay. So we are going to solve for this quantity IX in 2 different ways. We are going to brute force it by effectively throwing the kitchen sink at this problem. Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law, developing a series of relationships and all of that kind of stuff that will allow us to solve for IX. And then we are going to approach it using the superposition principle or superposition theorem. And we will see that for this particular circuit, the superposition theorem gets us the answer in a much easier way. And the result will agree 100% with what we found by using the more convoluted. Okay. So let's start with method number 1. What I'm going to call brute force or kitchen sink or whatever. It's throwing everything that we know at it. And just for simplicity's sake later on, I'm going to go ahead and make a copy of this. So because I'm going to be applying Kirchhoff's voltage law and Kirchhoff's current law, I'm going to identify some things that may be of use to me. I'm going to call this voltage here V6. I'm going to call this voltage V10. I'm going to call this voltage V9. I'm going to call this current I6. And I'm going to call this current I9. So at least with respect to my resistors, I have both the current and voltage through all of them taken care of. And then obviously I have my 6-volt source, and the current leaving the positive polarity terminal of that guy is I6. I have my 2 amp source, and the voltage drop over my 2 amp source would just be V9 plus V10 by using Kirchhoff's voltage law. So from these quantities, I should be able to figure out any possible thing I need. So what I'm going to do here is I'm going to write a Kirchhoff's voltage law equation around my left loop. So left-hand path. And I get -6 volts plus V6 plus V10 is equal to 0. And I'm going to write a KCL equation at my top middle node. So I'm going to say IX is the current flowing out. And that is going to be equal to my currents flowing in, which is I6 and I9. But by observation, I can see very easily that I9 is simply 2 amps. I am going to now write some Ohm's law relationships. That are going to relate my 2 equations, because right now I have 2 equations and 4 unknowns. So I could say that I6, actually, let's write it this way. V6 is equal to 6 ohms times I6. And I could say that V10 is equal to 10 ohms times IX using Ohm's law. Anybody have any questions, comments, or concerns about the relationships that we've developed here? So I'm going to substitute my Ohm's law relationships into my Kirchhoff's voltage law equation. And I'm also going to move 6 volts to the right-hand side of the equal sign. So that's going to look like V6. So 6 ohms times I6 plus V10, which is 10 ohms times IX. That is a poor looking X. Will be equal to 6 volts. And I'm going to rearrange this equation to move the constant term to the, actually, I'm just going to move I6 to the left-hand side from the way it's written currently. So I'm going to have negative I6 plus IX is equal to 2 amps. And so now I have 2 equations and 2 unknown quantities, and we're going to solve this system of equations. Now, this system is easy enough to where we should be able to solve it using substitution, but I am lazy and we have calculators for a reason. We're going to be solving systems of equations using our calculators a whole heck of a lot in this class, so we might as well start today. So this is a 2x2 system. Actually, I'm going to use my TI calculator because that's what I prefer for something like this. If you have any questions about how to solve systems of equations using your calculator, please hit me up and I will happily help you. So my coefficient for my first variable, I6, is 6 ohms in my first equation. My coefficient for my second variable, IX, is 10 ohms. My constant term is 6. My coefficient for I6 in my second equation is -1. My coefficient for IX in my second equation is +1. And my constant term is 2. Solving this system of equations, I find that I6 is equal to -7/8 of an amp. And IX, which is the quantity that we're looking for, comes out to be +9/8 of an amp. And for those of you that know how to solve systems using a calculator, you should get to this result pretty quick. So this is one way to solve this problem. It wasn't particularly hard, but I would argue it's pretty tedious because we had to wind up writing 4 separate relationships for everything, know how to put it all together. Know effectively that for the most part, the right-hand half of the circuit doesn't really tell us much information except that 2 amps is flowing. So there are lots of different things that we could do here to make this more complicated if we weren't familiar with this particular circuit. And I am, because I've been using it for 5 years at this point. Okay. So let's look at another method to solve this thing. Yes, sir. So that the current would be flowing, that 2 amps of current would be flowing into the positive polarity terminal. But since we didn't use V9, it doesn't particularly matter. I could have written it the other way, and we would have just figured out that it would have a voltage of -18 volts, positive polarity on the right. Yeah, or positive polarity on the left, excuse me. All right. So method number 2. Superposition. So because, go away menu. Because this source, or excuse me, because this circuit contains 2 independent sources, we're going to actually analyze it twice. All right. For our first case, we're going to say that our voltage source is on and our current source is off. So I'm going to paste my circuit here. I'm going to turn my current source off exactly how the superposition told me to do. So I'm simply going to replace my current source with an open circuit. Can anybody think about why an open circuit is used to turn a current source off? Because no current can flow through an open circuit. So this represents a circuit element, if you will, which forces there to be exactly 0 amps of current flowing through it. Right? So, excuse me. I'm going to be solving for what I'm going to call IX prime here, where I use this prime notation to indicate that this is my first iteration of superposition. What's IX prime? Analyze it. It's much easier than what we just did.
It's 6/6.
Yep. 6 volts over 6 ohms plus 10 ohms comes out to be 6/16, which is the same as 3/8 of an amp. Done with this particular iteration. Now we're going to look at the circuit with our voltage source off and our current source on. So I'm just pasting my circuit in here. I turn my voltage source off by replacing it with a short circuit because we know that 0 volt drop occurs across a short circuit. Excuse me. Now I'm going to solve for IX. How can I do that? Anybody have any thoughts on how we might do this analysis? Current division. This looks exactly like one of the examples that I worked in class last Friday, except with different numbers. Right? I'm going to call this IX double prime. And using current division, we could say that IX double prime is going to be 2 amps times 1/10 ohms divided by 1/10 ohms plus 1/6 ohms. So let's see, that's going to be 3/30 divided by 3/30 plus 5/30. So 3/8 times 2 is 6/8. And now bringing things together, IX should be the results from our first iteration of superposition, IX prime, plus the results from our second iteration. So that is 3/8 of an amp plus 6/8 of an amp comes out to be 9/8 of an amp, which is the exact same result we got working the problem with both sources on. Which circuit analysis was easier? I would argue applying superposition here. We were able to use just Ohm's law and a simple current division relationship to get the result instead of having to write 4 equations, interconnect things, and all that kind of good stuff. So this is how we apply the superposition theorem. I do want to point something out here, and I underlined it way back at the beginning. We can only turn off independent current sources or independent voltage sources. Any dependent source that's in the circuit has to be left on at all times. Can't turn that off. Okay. So now we're going to look at this from a different perspective. You guys have a question? All right. So now we're going to talk about linearity here. And if I am being honest, I don't think the other people that teach this class talk about linearity, which I think is an absolute travesty. This topic is critically important for electrical engineers. Biomedical engineers also happen to have a class on linear systems. I believe mechanical engineering students do as well. Not sure about chemical and the others. But this is something that's going to show up in a lot of different places for some of you guys as majors. And we are going to look at circuits in this little section of the class from a slightly different perspective. We are going to look at a circuit as a system that contains inputs or excitation signals and outputs or responses. And the superposition theorem is directly related to this concept. Okay. So in a very general sense, every circuit, or at least every linear circuit, can be thought of as a linear black box network. Okay. And we'll talk about what this means in a moment. And on the left-hand side of this linear black box network will be where I'm going to apply input signals. So generically, I'm going to call my inputs X. And on the right-hand side, we will have our outputs, which I will generically call Y's. X, our input, could be a current, could be a voltage. Y, our output, could be a current, could be a voltage. And this linear black box network acts on our input signals to generate our response. And it acts on these input signals by applying a system transfer function, h of x, such that h acting on x gives us y in a general sense. But we're going to split things up here a little bit because we have two inputs and two outputs, right? So we could say that H acting on this combination is going to give us Y1 plus Y2, and what I've drawn here, and those big spaces are intentional, is effectively describing what's going on in the superposition theorem. If I look at the input X1 by itself, it generates some particular output Y1. If I look at the input X2 by itself, the system generates an output Y of 2. And if I apply both of those inputs at the same time, I get a sum of the outputs from each source on individually, which is literally what we just did using the superposition. Where linearity is different, or where it's bigger than just superposition, is that there's also a scaling property or homogeneity property of linearity. Okay? So if I scale my input by a factor of alpha, my output also scales by a factor of alpha for a linear system. But I can scale my inputs by different factors. So if X2 was scaled by a factor of beta, then my output Y2 would also be scaled by this factor of beta. For any linear system, it will obey this response, which means that two distinct and independent properties are being satisfied. The first of which is the additivity property, additivity. This is nothing more than what we just talked about as the superposition theorem. And then we also have the homogeneity or scaling property. So let's take a look at the scaling property by itself. I'm going to take that same circuit, and to make our life easy, let's scale both of these inputs by the same factor, okay? So let's scale my voltage by a factor of 2. So instead of having 6 volts, I'll have 12 volts. And instead of having 2 amps, I will have 2 amps scaled by a factor of 2, which is 4 amps. Let's talk about what we expect the result to be. Okay. So if I scale my inputs by a factor of 2, according to the homogeneity principle of linearity, my output should scale by a factor of 2 as well. So we saw that for our original circuit, actually, I'm going to draw a table here. On the left-hand side is going to be my inputs, and on the right-hand side is going to be my outputs, right? So when I applied a 6-volt source and a 2 amp source, I found out that my response or my output was 9/8 of an amp. When I applied a 6-volt source by itself, I got an output of 3/8 of an amp. When I applied a 2 amp source by itself, I got an output of, well, it had to have been 6/8 of an amp, but let me just double check up here. Yes, 6/8 of an amp, right? So what I'm about to do now is I'm going to apply twice the 6 volts and the 2 amps. So what do we think the output is supposed to be? Nine over 4 or 18/8. Either way is fine by me. So this is what our expected output should be using the scaling factor or scaling principle when we're scaling both inputs, right? So let's analyze it and see that that's true. So once again, I'm going to call this voltage V6. I'm going to call this voltage V10. I'm going to call this current I6. Writing my KVL equation, I'm going to have V6, so 6 ohms times I6 plus 10 ohms times IX is equal to 12 volts. Writing my Kirchhoff's current law equation, I'm going to have IX is equal to I6 plus 4. I'm going to move the I6 to the other side. So that's going to give me negative I6 plus IX is equal to 4 amps. And I can solve this system. This is literally the exact same system we had earlier, except that both of our constant terms are now twice as large. And let's throw it in our calculator. Luckily for me, the TI calculators keep the equations stored, so I'm just going to change 6 to 12 and 2 to 4, and I get negative 7/4 of an amp and positive 9/4 of an amp. So what we've just verified here is that the scaling property happens to work for this circuit as well. So what I want to do now as a last little thing here is show that they both work simultaneously. So to prove that, we are going to scale each individual input by a different amount. Okay. So what do you guys want to scale the voltage source by? Could be a negative number as well, just 0.2, all right? So 0.2 times 6 volts. So with a scaling factor of 0.2 for our 6-volt source, what are we expecting the output to be with just the 6-volt source on? Whatever 0.2 times 3/8 of an amp is, right? So that would be 0.6 over 8. What do you want to scale the current by? -3. All right. So that means that we should have -3 times 6/8. So that is -18 over 8. Putting those together, 0.2 times 6 volts and -3 times 2 amps. That should be -17.4 over 8 amps is my output, if I did that math correctly. 0.2 times 3/8. And let's see. Yep. And then -3 times 6, definitely 18. 0.6 minus 18, 17.4. All right. So let's see if that shakes out. So 0.2 times 6, 1.2 volts. Polarity stays the same because the scaling factor was positive. This 2 amp source is going to get changed into a 6 amp source direction down because the scaling factor was negative. And let's write our equations again. This is going to be V6. This will be V10. This is I6. And when we write our Kirchhoff's voltage law equation, we're going to have 1.2 volts will be equal to V6 plus V10. Using Ohm's law, V6 is 6 ohms times I6. V10 is 10 ohms times IX. Writing our Kirchhoff's current law equation, we're going to have I6 is equal to IX plus 6 amps. So I'm just going to scratch that up here so I can do the math really quickly. So now we're going to have I6 minus IX is equal to 6 amps as our second equation. Let's solve these. So +1, -1, +6. I get I6 is equal to 153 over 40. IX is equal to -87 over 40. -87 over 40 is -2.175 amps. Just for the sake of argument, -17.4 over 8 is -2.175 amps, right? We were able to predict exactly what was going to happen in this circuit before we analyzed it because we knew what the response was to an arbitrary voltage input and an arbitrary current input. What this means, I don't suggest you do this, but what this means is that you could break any circuit down and replace every source with just 1 volt and 1 amp sources and know how everything is going to respond, right? If we can figure out what the output is for any individual source in a circuit is, then we can simply add up the results, right? So, let me pull up you guys' web work here real quick. I want to talk about some of the things here and we might work a problem. So this is homework number 5, I believe. Let's look at problem 1. This problem has nothing to do with superposition, so let's move along to the next problem. This problem, even though it only has a single source, you can use the scaling property in order to solve this thing, right? So let's take a crack at it, actually. What's going on here is effectively, in the first part, you're given a value of Ix, and you're asked to find the value of Vs. In the second part, you're given a value of Vs, and you're asked to find Ix. We only need to apply circuit analysis to one of these situations, and then we can use the scaling property to figure out the answer to the other one. So I think you guys would probably be more comfortable with doing part B first, where you're given a value of the voltage and you're solving for that current Ix as opposed to working backwards through the circuit. All right. So let's take a look at this thing. Vs is given to be 140 volts for me. Then we have 2 4 6 8 and I'm going to guess 10. Yep. Here's the Ix that we're going to solve for. You guys have any thoughts on how you might want to solve for this? Or you're going to let me have free reign? If you let me have free reign, I'm doing voltage division twice. All right. So effectively what I'm going to do here, I'm going to call this voltage V1, and I've drawn that dash line because I'm going to replace everything to the right of that dash line with its equivalent resistance for my first iteration of voltage division. Then I'm going to do blue. I'm going to call this voltage V2. Everything to the right of that blue dash line, I'm going to replace with its equivalent resistance when I do voltage division the second time. And then once I know that voltage V2, I can simply do Ohm's law to find the current Ix. All right. So REQ1 is going to be 4 ohms in parallel with 6 ohms in series with 8 ohms in parallel with 10 ohms, right? So 8 ohms in parallel with 10 ohms is 8 times 10 over 8 plus 10, 40 over 9, plus 6, 94 over 9. I'm going to store that as x, 4x over 4 plus x I get to be 188 over 65. Anybody wants to verify that, by all means, go for it. Always a possibility that I've made a mistake. All right, I'm getting at least one thumbs up. So from here, I can say that V1 is 140 volts times that 188 over 65 over 2 plus that 188 over 65. So that's 140 times what I have stored in my calculator is Y over 2 plus Y. Gives me what I'm storing in my calculator is Z. This is a giant fraction, 13,160 over 159 volts, or in normal people terms, 82.767 volts. Now I'm going to do voltage division a second time. V2 is simply what I have as V1 times 10 ohms in parallel with 8 ohms. Over 6 plus 10 in parallel with 8. Let's see, 80 over 18. 6 plus 80 over 18. Which comes out to be 5,600 over 159 volts, or 35.220 volts. And from here, IX is simply V2 over 10 ohms. $560 over 159 amps, or 3.522 amps. Just to make sure we've done things correctly here, throw this into WebWork and see if the robot agrees. I don't think it's really necessary to put that many decimal places in, but we're going to do it anyway. Correct. Yay, we did basic circuit analysis correctly. I should be able to do it by now, but then again, I do make mistakes. All right, so I would argue now that the hard part is over, right? We are not going to do any more circuit analysis to answer the other two parts of this question. We are going to use the scaling property of superposition. So in part A, we're told that IX is 160 milliamps, right? So this is IX for B. So what is 3.522 amps in our denominator? And then I think it was 140 milliamps here. What's this ratio? 0.14 divided by what I have as my previous answer is a factor of 0.03975. I'm going to multiply So Vx for part A is just going to be 140 volts times that 0.03975. Will be 5.565 volts. That's 160 milliamps, not 140. Yep, I got the 140 mixed up. Thank you. All right, let me fix this one real quick. I was about to say this should work because that's the whole point of it, but not if I enter the numbers in wrong. So thank you for that. 0.16 divided by 3.5220125, blah, blah, blah. So this is supposed to be 0.0454 and change. .360 volts. Try this again. Told you I make mistakes. There we go. No circuit analysis whatsoever. Only using the scaling factor, right? Part C here is simply to calculate the ratio of V over I. That's literally just simple division from what we've done, right? So nothing wild or crazy. All right, so I want to take a quick look at your in-class assignment as well. This is when I split it up into things. In-class assignment number 5. All right, so the reason why I'm taking a look at this in-class assignment is because I want to kind of explain what's going on here, right? So in part A, I asked you to determine the contribution of the 1 amp current source to the voltage Vx. That means I'm expecting you to analyze this circuit with the 1 amp current source on and your voltage source off. When you see determine the contribution of a source on your exam, that means do superposition. It's the only thing you're going to see on your test that explicitly tells you how to analyze a circuit. Okay, everything else is going to be free reign. Whatever you guys feel is the most appropriate way will eventually work out. But for superposition, you have to do superposition. So the only way that I can make you do that is telling you specifically, figure out what the contribution of a particular source is to that quantity. So for part A, leave the current source on, turn the voltage source off. For part B, leave the voltage source on, turn the current source off. For part C, do not do any circuit analysis whatsoever. Simply add the results of A and B together. For part D, do not do any circuit analysis whatsoever. Use the results of parts A and B and scale them appropriately based on the numbers that I've given you here to get the result. If you can do that, this stuff makes enough sense for you, for me. All right. So that is enough ranting out of me for today. Get at it. I think that's the only problem. And then you're free to get out of here.